Mathematical models and least squares analysis. Orthogonal subspaces. We've been spending quite a bit of time lately talking about orthogonal vectors, vectors that are perpendicular to one another. Now we want to take that same concept and look at subspaces. So subspaces are orthogonal when the vectors within the subspace are orthogonal to the vectors in another subspace. So for instance, we're going to let S1 be the span of the vectors 1, 0, 1, 1, 1, 0. And S2 be the span negative 1, 1, 1. Now just remembering what span means. We're saying that anything in S1 can be found by taking C1 V1 plus C2 V2, where this is V1 and this is V2. So in this case, we would be dealing with a plane, whereas span of negative 1, 1 would be a line. We're trying to show that these are orthogonal, which means if I have that plane, that line is going to be at a 90-degree angle to both of the vectors, which makes the plane. So let's take a look at 1, 0, 1 and negative 1, 1, 0. So again, we're checking them both against this vector. And this would give me negative 1 plus 0 plus 1, which is 0. And this would give me negative 1 plus 0, which is 0. So we can say now that S1 and S2 are orthogonal subspaces. This brings us to orthogonal complement. So if S is a subspace of Rn, then the orthogonal complement of S is the set of all vectors that are orthogonal to the subspace. So that's all this is saying. It's the set, this is called S perp, which just means it's the set of all vectors perpendicular to the subspace defined by S. So all of the vectors U such that the dot product is going to be 0. So in our last example where we determined that S1 and S2 were orthogonal subspaces, we can say that S1 is the orthogonal complement of S2 and S2 is the orthogonal complement of S1. Obviously, it's very easy to check whether or not two subspaces are orthogonal because we've already done that. We just checked whether the dot product was in fact equal to 0. It's a little bit harder, of course, to find the orthogonal complement. So that's what we're going to do now. We're going to find the orthogonal complement of the subspace S of R4 spanned by the two column vectors V1 and V2. So this is V1 and V2. And we're trying to find the orthogonal complement. We're trying to find S perp. Keep in mind that that means that A transpose U is equal to 0, or in other words, we're talking about the null space of A transpose. So here's how we're going to figure this out. We have A transpose. So here's A, V1, V2. We did A transpose, which is turning rows into columns, columns into rows. A transpose times U has to be equal to 0. That means we're really looking for the null space of A transpose. So how do we do this? Well, we know that this means 1x1 plus 2x2 plus 1x3 plus 0 is equal to 0. And 0x1 plus 0x2 plus 0x3 plus 1x4 is equal to 0. So that's these two equations. Obviously, I've taken that first equation and rewritten it so that x1 is isolated. And I can see that x1 depends on x2 and x3, and x4 is simply 0. So I'm going to let x2 be S and x3 be T. So again, we're talking about the null space, so we're used to finding the null space. And so I can rewrite this as x is equal to S times negative 2 and then 1 because x2 is equal to itself, 0, 0 because 0 in x4 and 0 in x3, and then T I've got -1 here. I've got 0, x2. I've got x3 is equal to itself, and x4 does not include anything to do with x3. So these are my two vectors. So again, what is the orthogonal complement? It is those two vectors created from this equation. So we just did the math. We determined that given the span of S, that S perp was two other vectors. Now, these four vectors total span all of R4, which means that any vector in R4 we can get to using V1 or V2 from S, or V1 or V2 from S perp, or a combination of those. So again, that's called a direct sum. A direct sum says let S1 and S2 be two subspaces of Rn. So this is S1, this is S2. Two subspaces of Rn. If each vector can be uniquely written as a sum of two vectors, S1 from S1 and S2 from S2, whereas x is equal to the sum of those two vectors, then Rn is the direct sum of S1 and S2, which means we can get to every single vector in Rn from the direct sum. Notice the notation. Here are a few properties of orthogonal subspaces. We are not going to spend a lot of time on these, but you can find the proof in your textbook. The reason that we're studying all this is we're trying to get to the least squares analysis, and that's what all of this will lead up to. But here are some important properties. So first, the dimension of S plus the dimension of S perp is equal to n. So we just found this in our two examples that we just went through. Our first example was from R3, and the two sets of vectors, S had two vectors and S perp had one vector, and that was a total of 3. And in our last example, we were dealing with R4, and S had two vectors and S perp had two vectors. And so again, that totaled R4. Next, Rn is equal to the direct sum of S1 and S2, which is just the definition of a direct sum. And then S perp is equal to S. What we're really trying to get to is a projection onto a subspace, and this will tie into finding the least squares analysis, or the least squares estimation. So if U1, U2, and so forth is an orthonormal basis. So again, we've talked about orthonormal basis. It's a basis, so it spans all of a subspace of Rn. And it's orthonormal, so all of the vectors in the subspace are orthogonal. And normal, meaning that they're unit vectors. Their length is 1. So if you have that, if you have U1, U2, and so forth are an orthonormal basis for the subspace of Rn, and V is a vector in Rn, then the projection of V onto S can be found using this equation. Now, this gets really mathy and wordy, so let's look at an example. But before we look at an example, what does this even mean to find a projection onto a subspace? Well, what we were doing before is we were finding an orthogonal projection onto another vector. So we had this vector and this other V, so this was V and this was U, and we said, okay, let's just go ahead and find some vector Z, or whatever we called it, I think we called it Z, that was orthogonal. So we had some value of V, so some scalar of V, and Z together made U. That was an orthogonal projection. Well, that's what we're doing here. So think of this, if I've got W1 and W2. Now in my picture, that's the blue one. Let me change colors to blue. That's this guy. And the orange one, I don't have an orange color. But essentially we're saying this is some plane. So no longer are we looking at just V1 being extended into a longer line. We're looking at an entire plane formed by two vectors. And now I want to find a projection of this line that's orthogonal down to this vector. So this is a projection onto a subspace. It's going to be an orthogonal projection, but instead of to some scalar of V, it's to some value on the plane. Let's take a look at the math now involved in this. And for now, you just have to stick with me because right now it just seems like, why are we projecting onto a subspace instead of a line? Eventually this is going to make sense because we are going to be using this process when we're dealing with least squares analysis. So thinking about projection onto a subspace, we have the vectors v1, v2, and we're projecting v onto the subspace of R3 spanned by those vectors v1 and v2. So it makes sense because we're dealing with orthogonal projections that we would use the gram-schmidt process, which we've already learned. So the first thing we're going to do is we're going to use the gram-schmidt process to find an orthonormal basis. And then we're going to do the projection of V onto S. So the gram-schmidt process, if you'll recall, says take V1 and divide it by the length of V1. And this is the alternate form. So just to make it easier. So this is V1, and this is the length of V1, 0 squared plus 3 squared plus 1 squared. So that's the easy part. And then, of course, I have to find U2. Oops, wrong one. This is U1. Then I have to find U2, but in order to find U2, I have to find W2. And W2 is V2 minus, we've got the inner product of U1 and V2 times U1. So V2 is 200. I'm taking the inner product of U1 and V2. So that's 0 times 2 is 0. 0 times 3 radical 10 is 0. 0 times 1 divided by radical 10 is 0. So I got a lot of zeros, and then I recopied U, which means this really is 0, 0, 0, and that gives me 200. So this is now W2, and this is the length of W2, which is 2 squared plus 0 squared plus 0 squared, or the square root of 4, which is 2. So notice I've just taken half of 2, which is 1, half of 0, which is 0, half of 0, which is 0. These are my two vectors in the orthonormal basis. Now we're going to find the projection. So we're using now U1 and U2, and we're taking V, the dot product of V and U1, so that's this guy, and with V, so that's 0 times 1, or 0, 3 radical 10 times 1, which is 3 divided by radical 10, and then 1 divided by radical 10 times 3, which is 3 divided by radical 10. That gives me 6 divided by radical 10. Now I'm just going to be distributing that, so that's 0. And then this is 18 divided by radical 100, which is 18 divided by 10, which reduces to 9/5. And then 6 times 1 divided by radical 10. It's 6 divided by 10, which reduces to 3/5. So that's where that first new vector comes from. And then I've got 1 plus 0 times 100, which is just 100. And now I'm adding these together, and this is my projection of V onto S. I'm going to do my best to help you visualize exactly what we just did. So the two blue vectors are the two original vectors V1 and V2. So in V1 and V2, we can see that the green vector, which is 1, 1, 3, which is vector V, is not on the span of the two blue vectors. So if you think about those two blue vectors creating a plane, we can see that this green vector v is not on that plane. It's not on the span of those two vectors. So what we were trying to do is we're trying to find a projection of this onto the span of v1, v2. So if you think about these two blue vectors creating a plane, we need some vector on that plane that is a projection. So again, we talked about what if the light was shining, the light would shine, we'd have some nice 90-degree angle vector that comes down here. The vector we just found is this purple vector. So we can see that if I drew a line at a 90-degree angle to the plane created by those two blue guys, we can see that the purple vector that I just drew, the one we just found, 1 9/5 3/5, that is on the plane created by v1 and v2. And if I drew a line from the end of the green vector to the end of the purple vector, that is orthogonal. So that is what we just did. The fundamental subspaces of a matrix. Let's take a look now at the 4 fundamental subspaces of a matrix. So recall, we know that if A is an m by n matrix, then the column space of A, or call A, or we're going to call it Ra, is a subspace of Rm consisting of all of the vectors in the form Ax, where x is some vector in Rn. So in plain English, we're saying it's the range of the vectors. So think about Ax is equal to B. We're looking for vectors x in Rn. So we've got an m rows, n columns matrix A. And then we've got an x matrix here that's x1 all the way to xn. And so this is A1, A2, da 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 da, A11, A12, A1M, and so forth, is equal to B, which is going to be, if you think about this being an n by 1 matrix, this is an m by 1 matrix. So that's what we're talking about, Rm. So we're talking about the column space of A. It's a subspace of Rm consisting of all of the vectors that can be created by A times x. That's what we're dealing with. So there's 4 fundamental subspaces that are going to be important to us. There's the null space of A, and there's the null space of A transpose. There's the column space of A, which is Ra, and the column space of A transpose. Let's take a look at how to find those 4 fundamental subspaces. So we're going to start using A, and we're going to find the column space of A, and the column space of A is found by finding those linearly independent vectors. So these two vectors, v1 and v3, are linearly independent, but 2, 0, 0, I can find by taking that first vector times 2. So we're not going to use that column in the column space of A. So the column space of A is the span of vector 1 and vector 3. How do I find the null space of A? Well, the null space of A, if you'll recall, is where A times x is equal to 0. So that's where I said x1 plus 2x2 plus 0x3 is equal to 0, and this is x3 is equal to 0. And so I can find the column space of A by doing exactly that. So x1 is equal to negative 2x2. x2 is just equal to x2, and x3 is equal to 0. So again, how would I write that? I would say x is equal to, we'll let x2 be s. So that would be negative 2x2, 1x2, and 0x2. So that is the null space of A. That is span of that vector. And now we repeat the process for A transpose. So the column space of A transpose I can find quite easily. I'm looking for the non-zero or linearly independent column vectors. And then again, the null space of A found in the same way we did the null space of, the null space of A transpose found in the same way. So x1 is 0, x2 is 0, x3 is x3, and x4 is x4. That gives me two vectors. Remember, that would be s and then 0, 0, 1, 0, and then plus t, 0, 0, 0, 1. So these are the four fundamental subspaces. So why is this important? Because we know that the column space of A and the null space of A transpose are orthogonal subspaces. And additionally, their direct sum is all of, in this case, R4. So let's think about the example we just did. The column space of A was 1, 0, 0, 0 and 0, 1, 0, 0. And the null space was 0, 0, 1, 0 and 0, 0, 0, 1. Looks an awfully lot like the standard basis for R4. And we could do the same for the row space of A transpose and the null space of A. And then again, the row space of A transpose and the null space of A would span all of Rn. In this case, that would be 3. What is a least squares solution? Now, what we've done to this point is we've done a lot of working with matrices and row echelon form or matrix equations, and we said we have ax equals b is some equation, and I can either solve it and get one solution, I can solve it and get infinitely many solutions based on some parameters, s and t, or I find that there is no solution, it's inconsistent. But in the real world, quite often, things don't work out perfectly. We have some situation that we want to model, and it's not a perfect solution. It's not in the column space of A if we were to set up an equation. But we want to find just the very best estimate that we can. So think linear regression or quadratic regression and so forth. We want to find the best estimate. So what we're saying is we have an inconsistent system, but we want to find the solution that minimizes the distance between AX and B. Now, what's B? B is some vector that is not in the column space of A. This is the column space of A. It's some plane. It doesn't have to be a plane. We're showing it as a plane, just for clarity. So we have some column space of A, and B is clearly not in the span of that. So anything in the span of that would be something on the plane. That would be within the span of A, or the column space of A. What I want to do is I want to find the point at which AX is going to be closest to B. And that point, we're just going to call it B hat. Now your textbook doesn't call it that, but I'm going to, because hat in statistics is all about an estimation, and that's what this is. This is an estimation to B, so that it's as close to B as possible. We're trying to minimize the distance between AX, which is our estimate, and B, which is our vector not in the column space. That is what we're trying to do, is we're trying to minimize that distance. How do I do that? Well, I bet you can guess. This is an orthogonal projection. So we're going to find this distance is the distance, the minimized distance, and we're trying to find this vector down here that is on the column space of A that's orthogonal to that distance. So let's talk about how to find x, because that's going to be important. We need to find x such that A times x is going to be equal to that B hat. So our estimate, that's this vector, is AX. We need to find x because we'll be given A. So if we know that A is just some matrix full of column vectors, A1, A2, and so forth to AN, and we know that these are orthogonal, then AI, each of these column vectors multiplied by this vector, which is AX minus B, those are all going to be, all dot products will equal 0. Why is that? Because they are orthogonal. Remember, these are orthogonal. So any vector in A multiplied by this vector ax minus b, which is just the distance between b and ax, or b hat, those are all going to be orthogonal. Now, what if I look at A transpose? If I look at A transpose times ax minus b is going to be 0 as well. And so let's take A transpose times ax minus b is equal to 0. And let's take the transpose, go ahead and distribute the transpose. So that gives me A transpose AX minus A transpose B is equal to 0. Add A transpose B to each side. What I'm looking for, or what I'm going to be using, is that A transpose A times X is equal to A transpose B. So again, this is a little jaunt into Dorkville, but here is the outcome. This is what we're going to be using in order to find X, and X is what we're trying to find, which is the least squares solution. So let's take a look at this practice question where we're going to use everything that we've learned. So we're going to find the least squares solution to the inconsistent system ax equals b, and we're given a and we're given b. Now, I don't have to check that it's inconsistent. If I did have to check it was inconsistent, remember all I would do is have 1, 0, 1, 1, 1, 2, 2, 1, 2, and row reduce, and I would end up with 1, 1, 2, 0, 1, 1, and 0, 0, 1. This tells me it's inconsistent because this is saying x1 plus x2, 0x1 plus 0x2 is equal to 1, which is impossible. So I didn't have to do that on this one, but I went ahead and showed you just in case you do have to check for inconsistency. Now I'm going to calculate A transpose A and A transpose B. A transpose A is, again, this is A. So A transpose is just turning rows into columns and columns into rows. So that's 1, 1, 0, 1, 1, 2. So I'm just going to multiply 1, 1, 0, 1, 1, 2. That's A transpose. I'm going to multiply it by A. 1, 1, 0, 1, 1, 2. And I end up with, this is going to be a 2 by 2 matrix. So I've got 1 plus 0 plus 1. I've got 1 plus 0 plus 2. I've got 1 plus 0 plus 2 and 1 plus 1 plus 4. So that gives me A transpose A is 2, 3, 3, 6. Now I'm going to do the same for A transpose B. A transpose B is, again, using A transpose. At this time I'm multiplying by B, which is 2, 1, 2. And that gives me 2 plus 0 plus 2 and 2 plus 1 plus 4, which gives me 4, 7. So these are the two that I'm going to use moving forward. This is A transpose A and A transpose B. Now that we have solved for A transpose A and A transpose B, we can set up our matrix equation. A transpose A times X is equal to A transpose B. And we're going to just simply solve that. So just as we have since we first learned how to do this, we're going to set this up as an augmented matrix. And we're going to do our row operations, and I'm just going to abbreviate them all the way down to reduced row echelon form. And we end up with 1 2/3. Now what this tells us is that X is equal to 1 2/3, and those values are coefficients in our least squares regression line. So if I want to represent the points that we're given as a least squared regression equation, I'm going to use x1, which is 1, plus x2, which is 2/3 x, So this is just a linear equation. Y is equal to 1 plus 2/3 x. In visualizing this part of the solution, we can see that these are the initial points we were given. 1, 1, 0, 1, 1, 2. We were given them in a vector form, but those are the ordered pairs. Those are the ordered pairs you can see graphed here. The equation we just came up with was y was equal to 1 plus 2/3 x, and as you can see, this is a good approximation for those 3 points. You might also ask to find the orthogonal projection of B onto A, and again, that is just using our equation, AX equals B hat, and this is A and this is X, those are the two values we already found, is equal to B hat. So all I have to do is do matrix multiplication. So I've got 1, 1 times 1, 2/3. That gives me 1 plus 2/3 or 5/3. And then I do the same thing for the next row, 0, 1. So that's 0 plus 2/3, which is 2/3. And then I do the same thing for the last row, 1, 2. So that's 1 plus 4/3, which gives me 7/3. So B hat is the orthogonal projection of B onto A. Again, I like to be able to visualize the solution. So in red, I have graphed both vectors of matrix A. So let's get rid of the green one for a second. And we can see that we could create a plane from those two vectors. And so let's just say that this is sort of a cross-section. This is the edge of that plane. There's no edge to a plane, I know. You get that this is the side of the plane that we are looking at from that side. This is vector B. So we can see that if we were to create a plane from those two red vectors, that vector B would not be on it. We can see the plane created by the red vectors would look something like this, and obviously B is not on that plane, and you can move it around all you want so you can see exactly what I'm talking about, but B would not be on that plane. Now, what we just found is vector V4 on my graph, which is the 5/3, 2/3, 7/3. And I want you to notice that this would be an orthogonal projection. Let me try to get you a good visual of that. We can see that the two red and the purple, those are all on the same plane. So this is the orthogonal projection. I could draw a line from the end of the green arrow to the end of the purple arrow. That line that I would draw would be, in fact, orthogonal. It would be at a 90-degree angle to the purple vector, which is on the plane created by the span of the two red vectors. The last part of this that you may be asked to find is the error. So recall what we're doing is we're finding a least squares solution. So the error would represent basically the distance from the plane created by the span of A and vector B. So we would essentially be finding the distance from B. So we're not finding the vector that is orthogonal, we're finding the distance of that vector. So to find the distance of that vector, we're just going to take AX minus B. So AX minus B, and I've rewritten AX for us and B for us. So 5/3 minus 2 is negative 1/3. 2/3 minus 1 is negative 1/3, and 7/3 minus 2 is positive 1/3. So what we want to do is find that distance, the distance of AX minus B, which would be the square root of negative 1/3 squared plus negative 1/3 squared plus 1/3 squared, which is the square root of 3/9 or 1/3, and that would be our solution. Typically, you would probably report that as a decimal, so you would just find the decimal equivalent for the error. The purpose in least squares analysis is to be able to apply this to real-world situations where the system would be considered inconsistent. So for instance, here we have a world population in billions for 6 different years, and we're assuming that the year is years since 1980, so we're going to use 5, 10, 15, 20, 25, 30. And we're going to write our world population in billions, so 4.9 billion, 5.3 billion, and so forth. So we're going to leave it just like this. We want to find the least squares regression polynomial. Now, we might not know if this is going to be a linear model or a quadratic model or a cubic model. Typically, you would go ahead and plot those points first and see what the data looks like. And then you could say, that looks fairly linear. Let's go ahead and find a linear regression model. Or in this case, they're asking us to just go ahead and go straight for the quadratic model. So using the quadratic model, we know it's some constant plus some constant x plus some constant x squared, all different constants. And we're going to use 5 and 4.9. So we're going to say y is equal to some constant that we don't know plus 5 times x plus 5 squared, which is 25, x squared. And then we're going to set it equal to 4.9. So we're using the 5, we're using the 4.9. And then we're going to continue for 10, 15, 20, 25, and 30. So you can see now that we have a system of 6 equations. We're now going to take those 6 equations and rewrite it as a least squares problem. And remember what that means is that we're going to set it up as ax is equal to b. So ax is going to be everything on the left-hand side, and b is going to be all of these solutions on the right-hand side. So it's going to look a little something like this. So it's 1c0, 5 x, 25x squared, and so forth. So we do that. We set it equal to c0, c1, c2, and then we have our solutions on the right-hand side. Now remember, what we did from this before is we said, let's find A transpose A, because our equation was A transpose A times x, and then is equal to A transpose B. So that's what we're going to do next, is we're going to find A transpose A and A transpose B. So let's do the math now, and we're just going to let Desmos do the math because you do not want to be multiplying all of this out by hand. So I went ahead and put in A and B just as they were. I'm going to find A transpose A, and I'm going to find A transpose B. Now we can see we've got a lot going on here, and that's okay because we didn't have to do this by hand. All I'm going to do now is I now have a new matrix equation where I have this matrix, A transpose A, multiplied by C0, C1, C2 is equal to this matrix. So I just opened a new instance of Desmos and made an augmented matrix, and I'm just going to row reduce that. So again, let Desmos do the work for you. So I'm going to row reduce this, and that gives me the identity on the left-hand side, and then 4.5, 0.08, and 0. That means in my equation, I have 4.5 is the constant, or 9/2. I've got 0.08 is the coefficient in front of x, and then 0 is the coefficient in front of x squared, which means this is not a quadratic model, this is a linear model. Then I went to just regular old Desmos. I plugged in my initial values, so again we used 5 instead of 1985 and so forth. And this is the equation that we came up with using the least squares model. And if you'll notice, that looks pretty darn good to me. Let's do just one more question. I would like you to try this one on your own. Feel free to use Desmos for everything. When you are ready, press play to see how you did. So first thing we did was know that this is going to be a linear model. And again, you can certainly graph it and take a look, but we've got 3 data points. We're probably not going to be able to come up with something quadratic or quartic and so forth. So that first column is going to be all 1s to represent the constant. And then the next column in A is going to represent the x values, -1, 1, and 3. The B vector is 2, -1, -2, which represents the y values. So remember, the first thing that we're going to do is find A transpose A and A transpose B, and we're going to create a new equation using A transpose A, X, A transpose B. So we're going to put that together into a new matrix, 3, 3, negative 1, 3, 11, negative 9. Reduce that, again, just using Desmos, and that gives me 1, 0, 2/3, 0, 1, negative 1, which means in my linear equation, 2/3 is the constant, and negative 1 is the slope. Going to Desmos, we can see that these are the points. They follow a negative linear pattern, and this is the equation we just came up with, and we can see that that does a fairly good job of representing the line that would be created by connecting those points. Up next is section 5.5, Applications of Inner Product Spaces.